In this video, we're going to be looking at how to differentiate very simple functions from first principles. So to begin with, what we want to have a look at is a straight line. A straight line has a constant gradient, or, if we prefer, its rate of change of y with respect to x is a constant. If we take the straight line y equals 3x plus 2, we can look at its gradient. We take 2 points and look at the change in y divided by the change in x. When x changes from -1 to 0, y changes from -1 to 2, and so the gradient is 3. No matter which 2 points on the line that we use, the value of the gradient is always the same. It is always 3. Now we can see that in another way by looking at a table of values. So let's take x ranging in values from -3 up to 3. And let's have a look at 3x, which is simply the values of x we've got multiplied by 3, and then add 2 to those values to give us the function y equals 3x plus 2. Now, as we look at this table of values, what we see is that for every unit increase in x, we always get 3 units increase in y. So as we go from -3 to -2, y goes from -7 to -4. As we go from 0 to 1, y goes from 2 to 5. For every unit increase in x, we get the same increase in y of 3 units. And so the gradient of this straight line is 3, or the rate of change of y with respect to x is also 3. Now, nice as it is that a straight line has a constant gradient and that y is changing at a constant rate with respect to x, this is not always the case. So, for instance, when you're in a car and you press the accelerator, you watch the needle on the speedometer, the needle doesn't go up gradually. It doesn't go up constantly. The rate of increase of the speed varies. Similarly, the acceleration due to gravity. Now, near the surface of the Earth, we assume that it's constant. But Newton actually showed that it was proportional to 1 over r squared, where r was the distance that we were away from the surface of the Earth. So we can see that as we move further away from the surface of the Earth, the acceleration due to gravity gets less. But it doesn't change constantly, it doesn't change uniformly. So, to see what's happening, we need to look at some very simple curves. For a curve, we can see that if we join any pair of points, we get a straight line. But when we join different pairs of points, we tend to get very different straight lines with very different gradients. We can see this again by looking at a very simple curve y equals x squared and looking at a table of values for it from -3 again up to +3. So now let's calculate the value of the function y equals x squared at each of these values. And now let's have a look how the value of the function is changing as the value of x changes. So if we have a unit increase in x from -3 to -2, we find that this time the value of y has gone down from 9 to 4. So it's gone down by 5 units. Not a problem if that decrease is going to be sustained. But when we look at the next unit from -2 to -1, we find that it's gone down from 4 to 1. Y has decreased by 3. And in the next unit it's decreased by 1, but then it starts to increase again. So we can see that for a very, very simple function like y equals x squared, y is not changing constantly with respect to x. Now this is not a problem so long as we can find a way of calculating it. To start that process, let's just have a look at a sketch of y equals x squared. And let me pick this point on the curve. Now, as we look at that, look at this very tiny little bit, that's almost straight. And if I was to home in and magnify, it would be almost more straight. And it would appear to be straighter and straighter. So that as we homed in closer and closer to the point, what we would see would be much more like a straight line. What straight line might we be able to take to represent that sort of local straightness? And the answer would have to be a tangent through the point. And that gives us what we need, because this tangent is a straight line. And we know that a straight line has got a constant gradient. And so this is the definition that we make. That the gradient of a curve y equals a function of x at a given point is equal to the gradient of the tangent to the curve at that point. So notice we haven't defined the gradient of the curve globally, so to speak. We've said that at any particular point, the gradient of that curve is going to be the same as the gradient of the tangent. So now what we want to see is how can we use this definition to help us actually calculate that gradient at any particular point. Let's take a fixed point P on our curve and a sequence of points Q1, Q2 and so on, getting closer and closer to P. We see that the lines from P to each of the Q's gets nearer and nearer to being a tangent as the Q's come nearer and nearer to P. So, if we calculate the gradient of one of these lines and let the point Q approach P along the curve, then the gradient of the line should approach the gradient of the tangent, and hence the gradient of the curve. So, let's now try and set up a calculation for the curve y equals x squared at the point x equals 3, so that this calculation represents what we've just seen. So first of all, I'll sketch the curve. So there is y equals x squared. Here we'll take our point where x is equal to 3. I'm going to take a point Q, which is near to P on the curve, and I'm going to join up those 2 points with a straight line. So there's my point P, there's my point Q, and I'm going to take a triangle formed by dropping a perpendicular down to reach the horizontal through P. So that will give me a little right angle triangle with the right angle at the point R. And now I'm going to take small values of PR. so that I get the coordinate of Q. So let's line that up. PR will be, first of all, 0.1, then 0.01, 0.001, and finally 0.0001. So what will be the x-coordinate of Q? X-coordinate of Q. Well, it will just be 3 plus whatever PR is. So that will be 3.1, 3.01, 3.001, and 3.001. Now I've got the x-coordinate of Q. Let's calculate the y-coordinate of Q. So that means we've got to square each of these. So our first result will be 9.61 when we square that. The next is 9.0601. The next, 9.00601. And the next, 9.0060001. So what's the change in y for each of these? In other words, what's QR? Well, we know that the base for where p is if x is equal to 3 at p, y must be equal to 9. So QR, the increase in y, we can get by taking 9 away from each of these. That's 0.61, 0.0601, 0.006001, 0.0006, 0.0001. So now we need to calculate the gradient of each of these little segments PQ. So what is that gradient? Well, it would be the increase in y, which is QR, over PR, which is the increase in x. So we've got 0.61 divided by 0.1. So to do the first one, I'll write it down. 0.61 divided by 0.1, and that is 6.1. If we do the same calculation here, the answer is 6.01. Do the same calculation here, and it's 6.001. And do the same calculation here, and it's 6.0001. So let's just have a look what's happening here. This gradient seems to be getting nearer and nearer to 6. And 6, perhaps by coincidence, is 2 times by 3, where 3 is the x value at this point P. So we need to do this calculation again, but we need to do it in general. So let's set that situation up. We take our axes and we plot our curve y equals x squared. Take my point P on the curve, and P is x, y. And I take a point Q a little further along the curve. How far along the curve is it? Well, I'm going to increase x by a very small amount. So we've got the same triangle as we had in the calculation. So there's R. And I am increasing x to get to R by a very small amount. And that small amount is going to be written as delta x. Now, I cannot emphasize enough that delta x is not delta times by x. It is a single symbol on its own, and it represents a small change in x. Well, what's that resulted in? It's pushed the point further along the curve to q, and so we've got a change in y of delta y. So that the coordinates of q are now x plus delta x and y plus delta y. Now, we've got the diagram labelled up, and so what we need to be able to do is do some calculation. But what do we know? We know that this is the graph of the curve y equals x squared. So here at the point Q, we know that y plus delta y is equal to x plus delta x all squared. And this we can multiply out. Will give us x squared plus 2x delta x. And I'm going to put that in a bracket to emphasize the fact that delta x is a single symbol, plus delta x all squared. But what else do we know? Well, we know at this point P that y is equal to x squared. So y plus delta y is equal to this, but the y part is equal to x squared. So that tells us, therefore, that the change in y, delta y, is this bit here. 2x delta x plus delta x all squared. So let's now calculate the gradient of this line PQ. The gradient of PQ, well, it's QR over PR, or the change in y, delta y, over the change in x. And we've got expressions for both of these. Delta x is delta x, and delta y is this. So we've got delta y over delta x is equal to, and let's remember that this was 2x delta x plus delta x all squared, and that was all over delta x. Now delta x is a common factor here. Let's take it out as a common factor. 2x plus delta x times by delta x all over delta x. Now delta x is a small positive amount of x, so we can cancel it out there and there. So we have delta y over delta x is equal to 2x plus delta x. Now remember what we're doing. We've calculated the gradient of this line PQ, and we're going to let Q come nearer and nearer to P along the curve. So we're letting delta x tend to 0 until this secant or chord PQ becomes the tangent. And so we can say that the gradient of the tangent at P is equal to, now we have to use some mathematical language, what happens to this expression as delta x approaches 0? Well, it would seem that if delta x got smaller and smaller and smaller and smaller and smaller until it got to 0, this would become 2x. We are approaching a limit of 2x. And so we use some mathematical language to help us say that. So we say that this is the limit as delta x tends to 0 of delta y over delta x is equal to the limit as delta x tends to 0 of 2x plus delta x, and if delta x is going off to 0, this is just 2x. And notice that agrees with what we had before when we said that the gradient was 2 times by 3 equals 6 at the point where x was equal to 3. Now, we could do this calculation in just the same way for all kinds of different curves, but it would become a bit of a bind if we had to keep writing this down all the time. So we have a special symbol for this phrase, the limit as delta x tends to 0 of delta y over delta x. And we write that as dy by dx. And we say dy by dx. And that's a symbol all on its own as a unit which stands for the limit as delta x tends to 0 of delta y over delta x. And in the case that we've just looked at, y equals x squared, dy by dx we've just seen is equal to 2x. Now, another video in the sequence will show how this is done for y equals sine x and the processes that we go through. We often use function notation y equals f of x. So in function notation, our point P, which was the point xy, becomes the point x f of x. Our point Q, which remember was x plus delta x, y plus delta y, well, this remains as x plus delta x for the x coordinate, but the y plus delta y, well, that's the function of x plus delta x. And so if we want to have a look at what we've done before, if you remember, then we take the change in y, that's delta y. So the change in y is what we had here at Q minus what we had at P. So that's f of x plus delta x minus f of x. And so our gradient, delta y over delta x, is f of x plus delta x minus f of x all over delta x. So dy by dx is the limit as delta x tends to 0 of the change in y divided by the change in x that gave rise to it, which is the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x. So if we're using the language of functions, that's the language that we use. And sometimes for functions, when we're differentiating them, instead of using the symbol dy by dx, sometimes use the symbol a dash to indicate that we've differentiated with respect to x. Let's just take one example using this notation. F of x is equal to the function 1 over x. Have a sketch of this curve for positive values of x. There it is, coming down like that. So if I take a point P, and I increase the value of x by a small amount to give me a second point Q on the curve, then I can see that in effect there's my delta x and there's delta y. So for all delta x still means a small positive increase in x, delta y just means the change in y, and we can see that this is actually a decrease. Let me complete this triangle by drawing in that secant PQ. And let's have these coordinates. This is x, y, and this is x plus delta x, and then f of x plus delta x. So let's have a look what we've got. Delta y is the change in y, and so it's f of x plus delta x minus f of x. And so delta y over delta x is f of x plus delta x minus f of x, all divided by delta x. And this is the gradient of this line PQ. Okay, what is f of x plus delta x? Well, f of x is 1 over x, so this is 1 over x plus delta x, minus f of x, which is just 1 over x, all divided by delta x. Here we have two fractions, and we are subtracting them. So we need a common denominator. And that common denominator will be x times x plus delta x. So I've multiplied this by this x plus delta x. I have multiplied it by x, so I must multiply the 1 by x. Minus, and I've multiplied the x by x plus delta x, so I must multiply the 1 by x plus delta x. And then this is all divided by delta x. So let's look at the top. X minus delta x minus delta x. So I've got x minus x, that goes out, and I've got on that line there minus delta x. All over. Well, I'm dividing by that and by that. So effectively, I'm dividing by both of them. So there we've got them both written down. Now, delta x is a small positive quantity. So I can divide top and bottom there by delta x, cancelling delta x out. So delta y over delta x is equal to minus 1 over x plus delta x times by x. And let me just multiply that denominator out. So I have x squared plus delta x times by x. dy by dx is equal to the limit, as delta x tends to 0, of delta y over delta x, which will be the limit, as delta x tends to 0, of minus 1 over x squared plus delta x times by x, equals. Now let's have a look at what's happening in this denominator. As delta x becomes very, very small, x times by delta x is also very, very small, and very much smaller than x squared. So as delta x goes off to 0, this term here goes away to 0 and just leaves us with the x squared. So our limit is minus 1 over x squared. And that's our calculation done in function notation to find the derivative, as we call dy by dx, or the gradient of the curve at a point. Now, the calculations that we've done are all quite complicated. You need to do one or two to practice the method and to see what's going on with it, to see how it's actually working. But to do most of your differentiation, there are a set of rules that you can follow that will help you do the differentiation much more quickly.